We have 4 kinds of steel samples. This is W1, which is a high carbon plain steel. W stands for water hardening. This is A2, which is a high carbon chromium and a few other things that you're going to find to look up. Tool steel. This is a low carbon, very low carbon. It's probably at 1009 or something like that, 1008. And one more. Where'd it go? W1. Now this is a medium carbon, and so here the 4th one is a medium carbon. This is a 1018 steel. You should write these things down because you're going to have to, if you want, because might be questions on your exam. Right?
So what was the first one? W1 high carbon?
W1 is a high carbon plain steel. It only has carbon, but it has about 1% carbon. And you can look that up. W1, it's a standardized tool steel. A2 is a high carbon, about 1% carbon, but it also has a considerable amount of chromium and vanadium, and so it is a much, we'll see that this stuff will harden by itself, just air harden. That's why the A stands for air harden. This also requires a little higher temperature. Right. And then we have a low carbon, which is, I don't expect to get any hardness out of this because we can't quench it fast enough. Pardon me?
I.
High?
I what?
I?
It's I.
What did I say?
I.
A2. Okay, you're behind me.
Oh.
I said that.
We're on the 3rd one right now.
We're on the 4th one. This is the low.
This is the
3rd.
3rd.
Okay, well, we'll say low carbon. This is a 1008 steel. Okay, and you have gone through these classifications, right, on your tooling unit, right?
Yep.
So you should be able to know when I say 1008, you should say right away that's a plain carbon steel, 0.08% carbon, right? And when I say this is medium carbon, where'd it go? Here it is. Medium. That's the
A3.
I have no A3. I have A2.
A2.
A2. Medium carbon. This is a 1018. So from your knowledge of the methodology, how much carbon is in this 1018 steel? Huh?
No.
18 what?
Percent.
18%. You're into graphite. 0.18. And don't forget the decimal point. That, even really high carbon cast irons like gray iron and that, they're only about 5% carbon. But the carbon, when you get up that high, 5-6%, it precipitates out of the iron in terms of graphite nodules, and that's why when you machine like gray iron, you touch it, it turns your fingers black from the carbon, from the graphite that's in there. So, just this short story. So, in order to make steel, we take iron oxide in the form of ore, right? And we heat it up with fluxing and a bunch of coal, carbon, actually coke, to pull the oxygen off, because the oxygen molecules have a higher affinity to carbon, generates this carbon dioxide, goes out the stack, and then we have this basically pig iron, which has like 7% carbon in it. You can't do a darn thing with that. I mean, it has a bunch of really hard things in it. So then you take that pig iron and you heat it up again in the old way, the old open heart stuff, and you add oxygen to it. So you take the oxygen out, replace it with carbon, and then we put oxygen back in to reduce the carbon back down to around less than 1% in most cases, right? And that's steel. So you put it in and you take it out. All right. Okay, so now we're going to do our as received tests, and you should write these numbers down after we get them. This is the diamond brow. It has a very specific geometry. You can't see it, but at the angle and the actual radius on the end is very closely controlled because it affects the reading. All right? And if you drop this thing, it's $300. You've got to get another one because you'll crack that diamond. I mean, you've changed the shape of the tip, and it doesn't read right anymore. Okay, so what are we going to do here? First thing we're going to do.
How would it crack if it's the hardest?
Well, it's hard, but it's brittle. Just like if you don't draw your knife blade down after you've heat treated it, it'll just break it because it's brittle. Toughness, hardness, and toughness are two different characteristics of the material. So diamonds are not tough. That's why. I mean, they've been cutting diamonds for hundreds of years, and they do it by just looking at it and finding a fault in the crystal and then whacking it, and it just cleaves right off. Then they would polish the facets. What do you polish a diamond with?
Diamond polisher.
Go get your diamond polish. Diamond dust. So they would they try to use a little hard. Diamonds actually naturally do not all have the same hardness. Some are harder than others. Okay. I don't want this one. I just, as another aside, here's a test block. This is a highly controlled piece of steel done by a Starrett, and it's in order to calibrate your machine. The last thing you ever want to do with one of these things is test it on both sides. See how somebody did that? Because that throws up a divot, and now it doesn't sit flat on the anvil, and you get false readings. Now, this has been repaired by grinding and lapping the drill. Just another side. We get our anvil and the right test block. Okay, we're going to use the C scale, which is needs a 150 kilonewton load, and it's indicated here. These are not even they're going to be really low, but I don't want to switch to B scale, which is the lower scale, and then go back to the C. I want just as a demonstration, we're going to do it all on the C scale, knowing full well that these samples are really too soft and they're not going to register very well on the C scale. Now, you got to have the right loading. We got the right loading. And I'm going to do a check on this. And this does two things. It shows us that the machine is operating correctly. and it also will load the, anything that's loose in there. And I just stuck that in there and thumb screw. What we want to compress everything, and the best way to do that is just do the test. So this is supposedly start check. It is 61.6 plus or minus 0.5 on the Rockwell C scale. And you just find a little spot, you don't need much, where there's no previous test.
How would you know how much pressure you put in?
Well, this machine will tell us when the preload is correct. Because the way this works, and you should know this because you've gone through the U-tooling U, is puts a preload on here, and then it releases a master load, and then it measures the difference in penetration between the preload and the finish of the master load. And that depth penetration is what it is then registered as a Rockwell C number, right? And it's basically a resistance to penetration, which is what hardness is defined as, resistance to penetration. So this is automatic, so when it gets up to around 6, I'm going to hear a beep. Let go. Now it's applying the actual load. $57.1, which means that it's just loaded the thing up. So we're going to do it again. We should get a higher number.
Where's the master load now?
That's a preload. What I just did is put a preload on. See how it went up? Because all the little parts are now loaded. So that is 61.3, and this thing is supposedly 61.6 plus or minus 0.5, so I'd say we're good. Right? So this machine is correct. Now we're going to test each one of these of our samples, and we're going to start with we're going to go from the high. Okay, we're going to start with the 8.2. All right, and you got to be sure that you don't have any burrs on this stuff. I'm going to take my file. Very important that your sample sit pretty flat on this ground anvil.
A2, is it a high carbon or low carbon?
This is a high carbon, and part of your job is to go online and look up A2 and get the specs on it. High carbon alloy tool steel. Okay, so like that if I overloaded it. 24, which is way low on the C scale. That's actually overlap between the C and the B scale. So we're going to do one more just to make sure we're not fooling ourselves. So we believe that. So 24 Rockwell C, that's the A2, as received for annealed. We'll put that over here. And now we'll do the W1. This is the high carbon, no alloy, or plain steel, but high carbon plain steel. When I say plain steel, I mean it has no other significant alloy elements in it.
Low carbon?
This is W1. W1.
W1.
W1.
Oh, all right.
This thing actually has an electronic or electrical lock on it, so supposedly keeps you from overloading it. Okay, it's 15.4. We're going to do one more. It's not surprising that this is softer than A2 just because of the carbon, the chromium in it. As annealed, it's a harder, tougher stuff. $19.4. That's close enough. What was the other one? 15?
15.4.
You can use an average of those two. Okay, that's that one. Now we're going to go to the medium carbon. So this was the this is the 1018, and this should be softer yet. $15.9, about the same actually.
What happens if you compress in the same hole?
Pardon me?
What happens if you compress in the same hole?
You get a really bad reading. Throw that out. It's not reasonable. Is it? 14.5. So we're going to call that good. That's the medium carbon, also known as 1018. Now this is the low carbon. This should be really low. But this is as received annealed state, so this is like probably a pearlite structure. And so once you're in a pearlite, a little change, difference in carbon is
And what was this one again?
low carbon. .7. It's barely reading. So, I mean, the readings, when you're this far down on the scale, you really can't, you can't take, can't use them very much, but we'll just, is for comparison, we can use it. Okay, so we have that all recorded, right? Okay, now I'm going to, I have a reluctance to leave this in here because it's so easy. We're not gonna, you know what I think we're gonna do is, we'll see how time goes, do the hardening, and then next week we'll look at the results, or if everything goes fast, we'll come back here and recheck it. Now I'm gonna need some help here. There's tools that we're gonna need are It's not my lab. So let's see. We're gonna start with the. Hey,
he went to go get it.
Okay, we're gonna do. We're gonna do the W1 first. Now we gotta get our. Here's our temperature control chart, right? So, as you saw from our little very short abbreviated lecture, we need to get this up to at least 1450. That's the temperature you can go at transition. And if you go a little bit higher, okay, now more oxygen, no. Back off the oxygen. That's it. Okay, something like that. All right, that's it. Okay, now there. Keep that baby up. Not too close.
W1.
All right, here, everybody, look at these things, and you guys tell me when you think we're there. Get the size too. Don't melt it, you're melting it. Okay, we're not melting. I don't know if we have enough to be able to measure it.
have to get this a little hotter because of the carbon, because the chrome. This is actually should be 15 something. Okay. Let's go.
Grinding, did you just soften up the middle?
No, I was, if I can hold it in my hand. But you do have to be careful about that on plain carbon steel.
Oh, yeah.
Hardness. Hardness. See how hard it got. Heat treatment. Right now, we can order all of them.
So we've already calibrated this, but what I am going to do is just take a sample. Pardon me?
No.
No.
They're the 4 examples we had.
They're all different.
The 10, 18, A2, W1.
Don't, this is just a test to push the thing together. So the first one we'll do is A2. Okay. So our A2 sample. Huh.
49.1?
49.1, which is not good. Something happened here. This is the A2, is it not?
Yeah, it is.
.5. So, what we might be dealing with here is decarburization because of the way it took so long for it to cool down. So we had a lot of time for the oxygen in the atmosphere to pull the carbon out of the surface. So we're gonna, but put that down. I mean, that's kind of what we had. We'll do one more, just
satisfy ourselves that we're not.
That's for the A2.
This is A2 now. If we had done, if this was, if everything was right, it should have been up in the 60s, 60, 61. Even lower, 44.2. So, go ahead, use those. That's the A2. And the next one we're going to do is, if I can read it. We'll find one that we can read. Okay, this is a medium carbon.
Yeah, dude. Only thing outside the roof or the cap. The cap marks are still there.
41.8. Medium carbon. Remember, this was. So the other thing that could have happened with the A2 is that since it's so small and doesn't have much of a surface area, that it could have been actually too slow. You know, oftentimes on air cooled, they'll actually put it on a grate and have a fan underneath it. 41.6. That's pretty consistent, right? Now, what was the first one?
41.8.
This was 41.6. So now we're going to go to the.
I don't know, dude.
He's also. He all texted me last night.
Okay, this is the W1,
No.
and I'm hoping we can get a reading out of it. This is the W1. Let's make sure that it's the W1. Didn't I say we started with W1?
Yeah.
Okay, so this is the W1 because it's the one that's slightly melted.
Is that like a really bad melt?
Well, you don't want to melt your heat treatment parts. It kind of like makes it doesn't work.
So the reading is be off of that.
No, I mean, you just put all this money in machining this part and then you melt it in heat treatment? $66. That's not unusual. W, the water, high carbon water quench tool, plain carbon actually get very hard. The problem is that they don't retain their hardness at a very high temperature. Sometimes it's only like 300 degrees, 200-300, and it starts dropping. So that's one of the reasons that knives are made out of water hardening steel, plain carbon, is because you can get them really nice and hard with a flame.
This is W1?
This is W1. Yeah. We're going to try one more spot here.
How much carbon is W1 now?
That's for you to figure it out. Look it up. That's part of the lab. $66. Oh, good and hard. Well, just one more on this one because that is even a little higher than I would expect. Rockwell C. Make sure you get that right. C scale. Rockwell hardness C scale. $65.7. All right. That's the W1. So what we have left is low carbon. All right. Let's see what we got going on here. $29.9, and this was what, 9 originally? So let's do one more. So it did harden some. Yeah, but still that's soft. But sometimes you can use that just as a toughening for certain parts. Ooh, 35.1. I'm not sure I believe that.
Tougher. The more you charge them, get stronger. So go ahead and use those numbers, and then you have to. There's a sheet that's posted on that has the composition of this material, right? And so use that. And so the lab, as it's explained, is for you to take these numbers and decide what happened. Was it quenched fast enough? Did we have it hot enough? Was it too slow? I mean, the TTT on this A2. It could be a combination. Maybe we didn't get it hot enough, because this requires a significantly. You have to look it up, and it'll tell you what the heat treatment temperature is. And then maybe the air cooling was because of the small surface area was maybe a little too slow. All right. Okay. Well, let's see. I'm going to keep these together. Let's see what time it is. Ooh, I don't have my. What time is it? It's getting out. They got to fix them.
7:30.
7:30.
11:30.
Oh, 11:30. All right. Well, I think we're don't have enough time. I think what I might do, maybe myself or we'll save it for next week, is we'll take that A2 and we'll just reheat treat it. But this time I'll just polish it up so it doesn't have black all over it. But instead of just sitting it, we'll blow it with some air.
Do you want this in slide or so? How do you want this slab?
Oh, and a document it's a document. It's on a MS. Just something I can open. You can use a PowerPoint if you want. but it's actually just like a little paper report. So let's say, you know, I'm the chief engineer and you did this for me. I want to know what you did and what happened.
Summary, everything we need.
Yeah, but of this, but